Okay, so we have quantum numbers. And as I stated a while ago, these videos are definitely will help you prepare for the exams, but you need to be using it in conjunction with your textbook as well to fill in any of the gaps. You know, I'm solving the problems, but if you're ever wondering, well, why is he doing that? You know, or where did that come from? It's definitely in the book. So I can't cover every single detail in these lectures. That's not what they're for. They're for working with the problems as if you've gone through the textbook and have a pretty good understanding of the material. Okay, so I'll write all sets of quantum numbers possible for electrons in the n is equal to 3 energy level. Okay, so the rule is then, if the principal quantum number is 3, then the angular momentum quantum number L can have values of from 0 to n minus 1, or 0, 1, and 2. So if we put them all in, I'm not sure if I'll be able to, I'm going to just do this. And maybe I can make a second column if we need it. Okay, so n is always going to be 3 here. And it can be 1, 2, 3 on up, but they say 4, 3. So if we take L to be 0, what we're going to do is every single set, and each set that I draw, each 4 numbers represents one electron, or one state that an electron can be in. Now m sub L goes from negative L through 0 to positive L. In the case of when L is equal to 0, then m sub L can only be 0. And then m sub S can be plus 1/2 or minus 1/2. And that's it. So we'll have plus 1/2. So the second set would be minus 1/2. So that's the only difference. So the n represents the energy level. L represents the orbital. M sub L represents the orientation of that orbital in space, and then M sub S is the spin of the electron in that orbital. So we have this first part, 3, 0, 0, represents your one orbital, and then there's 2 possibilities for the electron in that orbital. It can be spin up or spin down. When L is equal to 0, we also call that S. So that when you're labeling things, it's better to be able to switch back and forth between letters and numbers than to just have a whole set of numbers. So that's why they did this out. This orbital would be 3s. That's easier to look at than the 3, 0 orbital. Okay, so we should know that. I'm just going to list them over here because we'll need them for the next few lectures. This will always be 3, so L can be 1. M sub L can be from negative 1 to 1. So we'll just make it negative 1. So here's another possibility. So again, all of these are indicating, labeling the electrons that we can have, the possible states. So that's it for 3, 1, and negative 1. So 3, 1, and 0. You can see that we get 2 for each of them because each of these 3, 1, 0 represents an orbital. And it can be plus 1/2. The electron inside of it can be spin up or spin down. 3, 1. Okay, so let me just start breaking these up. Then we have 3, 1, and plus 1. 3, 1, plus 1, and negative 1/2. So those are all the ones that we can have. L is equal to 1, and when L is equal to 1, that would be a p orbital. It would represent a p orbital, and then we can have L is equal to 2, and that is a d orbital. So I might run out of room, but we'll have 3. I think I'll shorthand it now. So this is 2 minus 2, and then it can be plus or minus 1/2. I won't do that. I think I'll just write them all out. Make sure that there's no mistakes. 3, 2, and then minus 1 is a possibility. Minus 1/2. And I'll just grab a piece of paper here to continue on. Then we can have 3, 2, 0, plus 1/2, minus 1/2. then we can have 3, 2, and 1, plus 1. You don't have to put the plus on there, I'm just trying to distinguish between them, the minus 1 and plus 1. And then we can have plus 2 and plus 2 with a minus 1/2. So each of these sets, each 4 numbers, represents one state that the electron can be in. So we've drawn out all of the possible states that an electron can be in the third energy level. On the exam, it's doubtful I'd go that far. I might ask you to do out might ask you to do out n is equal to 2. Who knows? There's a lot of different ways of approaching it. That's why I'm doing out all the possibilities. So L, instead of using 0, 1, 2, 3 for L, we can call it S, P, D, and F. They represent the same thing. It's just, as I said, it's when you have those letters, it's a little easier to distinguish when you're trying to name these orbitals, the energy level and the type of orbital. To use a number for the energy and a letter for the orbital. Okay, each of the following sets of quantum numbers is incorrect. Here's another way of going creating a problem for this type of stuff, for the quantum numbers. So we have, and then it says each one is incorrect in some way. Explain what's wrong. So n is equal to 1, L is equal to 1. That can't be. L has to be 0 to n minus 1. Since n is 1, then the greatest that L could be is 0. And there might be more than one thing wrong here. Everything else looks good. N is equal to 4, L is equal to 3, that's fine. But m sub L can only be from -3 to +3. So if this were -3, that'd be fine. N is equal to 17. That seems like a large number. That's okay though. N can be any integer above a 1 or above. L is equal to 5. That's going to be less than 16, so that's fine. M sub L is 3, and M sub L in this case can be from -5 to +5, so that's fine. This one is the thing that's wrong. The spin on an electron can only be +1/2 or -1/2. Can't be 1. And then this last guy here, n is equal to 124. Wow, that's huge, but that's fine. It's just a very large energy level. L cannot be negative, so L can be anything. We can make it 66. It'd be fine here. Glad I chose that, because then m sub L is 53. That's certainly possible as well. So after making those corrections, those sets of numbers are now ones that would represent electrons in a hydrogen atom. Actually, in any atom, I should say, but definitely in a hydrogen atom too. Draw an s orbital, p orbital, and a d orbital. An s orbital is a sphere. Now the reason I'm putting a little more detail into it is when I draw it on the board, I would draw it for years with just a circle. And students, some students saw it as that's what its shape is. It's a circle. It's like a plate, but it's a sphere. P is a dumbbell shape, and it's also three-dimensional. You know, it's like two balloons stuck together. And then the d orbital is like four balloons stuck together. It looks like a four-leaf clover. And then there's one that has a different shape to it. But if you draw this, that's fine. The other d orbital looks like this. It's a little tricky, kind of cool-looking one, but the other five look like this. Okay, and then the last thing is show the difference between a 1s orbital and 2s orbital. 1s orbital, you have the nucleus, and then you have the electrons around on the outside, and they're free to roam around anywhere inside. But inside a 2s orbital is going to be larger, and then there's also an area that is empty of any electron density, and this is called a node. And then so there's electron density above, and there's electron density near the nucleus, but there's a spot where there's nothing. There's no electron density. But for a 1s orbital, the electrons are free to roam around anywhere. So the electrons can, in the 2s, will have one node, 3s will have two nodes, and these areas where there's no electron density. And that's true for all the orbitals. This one is easy enough to draw. When you get to p orbitals or d orbitals, it gets to be really tricky to draw all of those nodes and to show what's going on. And even if you were able to do it, very few people would understand what they were looking at. Here, this is fairly basic. There's a one node where there's an area where there's no electron density.